Have you ever imagined what it would be like to board a spacecraft and leave behind Earth's familiar blue-green glow, venturing through the dark void toward the worlds dotted across our solar system? The trip to the moon, just over there at 384,000 kilometers, took 3 days back in the Apollo era. A lot of people think, well, if 3 days was enough to set foot on the moon, how long would it take to reach our planetary neighbors? 10 days? 20? A month at most? The truth is far more striking. Get ready. Today, you're going to find out, planet by planet, how long it would really take to get there, and why every minute on board would be an extraordinary feat of human engineering. By the end, you'll look up at the night sky with fresh eyes, and if you enjoy this journey, go ahead and give it a like, subscribe to the channel, and hit the bell so you don't miss any space adventures. Before we map our routes, we need to talk about orbits. Planets don't trace perfect circles, but ellipses. Sometimes a body is closer to the sun, perihelion, and other times it's farther away, aphelion. They also don't move at the same pace. The farther a planet is from the sun, the slower it travels. Imagine planning a bus trip when all the bus stops are in motion. That's how interplanetary missions work. Heading straight toward your target makes no sense, because by the time you arrive, the destination has already moved. That's why engineers use curved paths like a Hohmann transfer. A single push sends a spacecraft onto an orbit that meets its target at just the right point, saving fuel. When possible, we combine this trick with a gravity assist. The spacecraft swings by a planet or moon, steals a bit of its orbital energy, and gains speed without burning extra propellant. How long would it take us to get to Mercury? It sounds simple, but behind that curiosity is a planet that, despite being the smallest in the solar system, holds essential clues to the cosmic childhood that shaped everything around us. Because it hugs the sun, Mercury works like a window into the past. Its crater-packed surface, traces of ancient volcanism, and an active metallic core that sustains a surprisingly strong magnetic field for such a small world. Investigating that field, understanding the composition of the interior, and deciphering the scars in the crust isn't just curiosity. It's a direct way to shed light on how planets formed and evolved. Even the possibility of liquid water in the past, as extreme as it sounds, has already been raised. If that ever happened, it opens a fascinating door to ask whether conditions favorable to life could have briefly emerged, even if only for a short time. But before we study anything, we have to get there. And the trip depends on a set of variables: speed, the distance between planets, type of propulsion, and, above all, how to brake at the right moment. As a reference, the Parker Solar Probe has already exceeded 692,000 kilometers per hour, 430,000 miles per hour, in its close passes by the sun. Even so, on an optimistic trajectory, it would take us more than 4 months to reach Mercury. Why? Because the distances never stop changing. In elliptical orbits, planets move closer and farther away. There is no single fixed distance between Earth and Mercury. When they're on the same side of the sun, in the alignment called inferior conjunction, the route shortens and can drop to something on the order of tens of millions of miles. In other geometries, the separation grows a lot. Mercury, by the way, has the most eccentric orbit in the solar system, eccentricity approximately 0.21, while Venus is much more round, eccentricity approximately 0.06, and that alone scrambles all the calculations. In practice, nobody points a rocket straight at Mercury and hits a button. You have to choreograph the journey like a physics ballet, use launch windows, transfer trajectories, and, almost always, gravity assists. That's how the missions that have gone there did it. In 1973, Mariner 10 used a gravitational boost from Venus and took about 6 months to its first Mercury flybys, delivering the first close-up images. Decades later, Messenger, 2004, ran a marathon of maneuvers with Earth and Venus before finally entering Mercury orbit, a feat that took roughly 6.5 years of travel and another 4 years studying the planet until the fuel ran out. Today, Bepi Colombo, ESA/JAXA, launched in 2018, is on its way, using solar electric propulsion combined with multiple gravity assists with Earth, Venus, and Mercury itself, to only then settle into the destination. Notice the pattern. Flying fast is easy. Entering orbit is hard. To orbit, the probe has to arrive slow enough relative to the planet to be captured by gravity. And in a vacuum, braking is energy expensive. Can we shorten the trip? Partly. Gravity assists move the clock forward, but they demand surgical precision. Mistime it and the spacecraft will miss the assisting planet. And unlike Earth and Mars, Mercury doesn't offer a robust atmosphere to help brake with aerobraking. The descent relies almost entirely on engines. Add to that the extreme thermal challenge near the Sun, and you see why long-duration flights end up being, paradoxically, the more economical path. When the question shifts to Venus, the glow gets brighter and the story heats up. Literally. Venus is the brightest object in the sky after the Sun and Moon. It shines because its atmosphere reflects a lot of light, and because, cyclically, it comes very close to Earth. But again, close is a moving picture. Orbits are elliptical, and alignments vary. At inferior conjunction, when Earth and Venus are on the same side of the Sun, the distance drops to a minimum that repeats in patterns of about 8 years, thanks to the almost periodic dance between the two planets. Over time, the average distance varies a lot, so no one serious answers. What's the distance to Venus with a single number? What we can say is that Venus has the most circular orbit among the planets, and because of that, its behavior is more predictable than Mercury's. Why go to Venus? Besides being the hottest planet, surface pressure approximately 92 times Earth's and oven-like temperatures, it may have been habitable billions of years ago, until a runaway greenhouse effect dried the world out and turned the crust into a geological pressure cooker. To probe that past, humanity has sent a lot there, with a historical success rate that actually surpasses Mars. The Soviet Union's Venera 1, 1961, was the pioneer on the way, but lost contact early. It's estimated to have passed about 100,000 kilometers from the planet after 97 days of flight. Mariner 2, 1962, made the first successful flyby in 110 days. In 1978, Pioneer Venus 1 entered orbit after a 198-day journey. ESA's Venus Express, 2005, traveled for 153 days before settling around the planet. Why so much variation? Because arriving isn't the same as staying. Flyby missions can take faster routes. To orbit safely, it's common to adopt longer, more fuel-efficient paths. On average, successful trips to Venus landed somewhere between about 4 to 6 months, with records around 109 to 110 days and longer routes near 200 days. Aiming high with more efficient engines, nothing prevents talk one day of 60 to 80 days. But landing and surviving on the surface is another chapter. The only images of the ground came from Venera 9 and 10, which lasted 53 and 65 minutes before succumbing to heat and sulfuric acid corrosion. When the destination is Mars, the question changes tone. Beyond how long, it becomes how and who. The path to the Red Planet has been blazed in both cooperation and competition by NASA and SpaceX. The former makes safety and redundancy its North Star. The latter bets on tech leaps and aggressive reuse, and interestingly, these visions complement each other. Distance. In 2003, Earth and Mars came within about 56 million kilometers, one of the closest approaches on record. In other periods, the separation more than doubles. If we play with the speed of light, travel time would vary from something like 3 minutes, when they're closest, to more than 20 minutes, when they're farthest, on average about 12.5 minutes, for a photon. For real spacecraft, the game changes. New Horizons, on its way to Pluto, left Earth at approximately 58,000 kilometers per hour. At that pace, Mars could be reached in about 162 days at average distance, roughly 289 days in the worst conditions, and in a very favorable alignment, around 39 days as a theoretical number. And if we used Parker Solar Probe's peak speed, in pure hypothesis, in the closest scenarios, the math drops to about 93 hours. In the farthest, close to 29 days. But that's a thought experiment. Real trajectories aren't straight lines, and cutting through the sun isn't on the table. In real life, engineers use a Hohmann transfer, the elegant ellipse that leaves Earth's orbit and kisses Mars's, with a launch window every 26 months. It's the most efficient method we know. The trip usually lands around 9 months, and a round-trip plan, with stay and return window, can total up to 21 months. Trading efficiency for speed means burning a lot more propellant and reducing payload, and still dealing with the psychological impact of months in a tight cylinder, far from Earth. That's where the Raptor engines and Starship come in. Very high thrust, reusability, lower costs per attempt. If those pieces deliver what they promise, How Long to Mars stops being an almost insurmountable barrier and becomes a matter of scheduling, budget, and acceptable risk. And why would anyone choose to go to Jupiter? Even without a solid surface, the solar system's largest planet is a living laboratory, continent-scale storms, a colossal magnetic field, and, above all, a moon system that looks like a miniature solar system. Europa, Ganymede, and Callisto may hide global oceans beneath ice, perhaps the best place to look for life beyond Earth. But is it far? Because Earth and Jupiter run on different tracks, the distance between them varies. In the best configurations, about 365 million miles. In the worst, near 600 million miles. On average, around 483 million miles. That's so much road that if you drove at 110 kilometers per hour without stopping, you'd need centuries. The trip depends again on alignments and on how much energy you invest to speed up and, especially, to slow down. Looking at past missions helps set expectations. Pioneer 10 was the first to arrive, direct route about 640 days. Pioneer 11 and the Voyagers also went fast and passed relatively close, tens of thousands of kilometers. But they didn't stay. They used Jupiter's gravity as a slingshot to gain speed toward the outer solar system. Galileo was patient. Almost 6 years to enter orbit on a VEGA-style route, Venus-Earth gravity assists, to arrive at the right speed and remain there for years. Time and fuel paid up front in exchange for high-quality science. In 2006, New Horizons cut the path in about 405 days to Jupiter, using the giant's push to accelerate toward Pluto. The pass even added a bonus of approximately 8,700 miles per hour to its speed. And today, Juno is studying Jupiter's magnetic field and interior up close, on a plan that also required patience to enter and maintain orbit. Talking about humans out there exposes current limits. If we generalize efficient trajectory math, a leg to Jupiter can take nearly 6 years. Just for food, the classic estimate for 4 people passes 8,000 pounds per year. Something like 48,000 pounds for the trip out, not counting the return. Add water, air, radiation shielding, and trucks worth of electronics. Protection against energetic solar particles and cosmic rays demands mass and engineering, and the psychological effects of such a long confinement, with Earth a pale point in the window, are real. That's why, while logistics for mature crews aren't dialed in, we keep investing in robots. In the short and medium term, 2 missions should light up our curiosity. NASA's Europa Clipper, with launch planned and arrival around 2031 after a long route to enter Jovian orbit safely, and ESA's JUICE, which launches, makes its assists, and arrives around 2029 for a dedicated tour of the icy moons. Again, note the pattern. To stay, the trip takes longer. To pass by, it goes faster. And Saturn? Who hasn't looked through a small telescope and been left breathless by those perfect rings? They hide questions that don't fit in a single video. How they formed, why the colors vary, why the planet glows a little on its own. How many more moons will surprise us? The icing on the cake goes by the names Titan and Enceladus, one world with seas of methane and another moon that vents plumes of salty water. But the first question is still distance. Again, everything changes all the time. In the best case, around 1.2 billion kilometers. In the worst, more than 1.7 billion. Cassini, which spent 13 years writing Saturn's encyclopedia, didn't go straight. It made 2 Venus flybys, returned to Earth, got a push from Jupiter, and only then dove into the realm of rings. Pioneer 11 took more than 6 years. Voyager 1, in an excellent alignment, arrived in about 3 years and 2 months. Voyager 2, in about 4 years. Cassini ran a 7-year marathon to arrive already at the right speed to be captured. New Horizons, on a passing trajectory, set a record. Roughly 2 years and 4 months to cross Saturn's orbit. The reason for the differences is already clear. route, number of assists, engine power, and, above all, the need, or not, to brake for orbit. And people? The same math that makes Jupiter hard makes Saturn even harder. Crewed means multiplying mass, bigger capsule, stores, life support systems, redundancy, shielding, instruments. Some encourage the imagination with estimates that a human itinerary could take 8 years to arrive, and the return would depend on a ballet with Jupiter in a perfect position for a slingshot home. Not to mention the radiation package, the stress, and everything we're only now relearning to manage with the Artemis program. That's why the most logical path for now is still to send robots and learn from them, step by step. At the outer limit of the giant planets, a pair of bluish worlds show up that look like twins at first glance, but tell different stories when you get close: Uranus and Neptune. Today we know that blue here doesn't mean oceans, it's chemistry. An atmosphere of hydrogen and helium, seasoned with methane, ammonia, water, and hydrogen sulfide, absorbs red and returns that blue-green hue. Uranus in particular is a collection of oddities. It spins on its side, with its axis tilted approximately 98 degrees, has a magnetic field misaligned by almost 60 degrees and offset from the center, and seems to shed little internal heat, something that may relate to a major past impact, jumbling the internal layers and even explaining the more washed-out tone compared to Neptune. Voyager 2's images in 1986 showed a serene disk, almost no bands or obvious storms. Infrared telescopes later revealed the calm isn't total, but Uranus is still the least turbulent of the club. Neptune, on the other hand, is pure dynamism, winds up to 1,700 kilometers per hour, large dark spots that appear and vanish, and a stirred-up atmosphere that prevents the photochemical haze from forming the way it does on Uranus, where it mutes contrast. The moons tell the other half of the story. Miranda, Ariel, Umbriel, Titania, and Oberon, the 5 largest of Uranus, show young surfaces, giant escarpments. Verona Rupes may offer more than 20 kilometers of freefall, and signs of cold geology made of ice and water instead of molten rock. When we look at exoplanets, we see why all of this shot up in priority. Ice giants like Uranus and Neptune are common around other stars. Understanding our blues is understanding other planetary systems. That's why the scientific community has pointed the spotlight at a mission that already has a nickname: Uranus Orbiter and Probe, a dedicated orbiter with a probe to dive into the atmosphere. The most favorable launch windows fall around mid-2031/2032, using Jupiter for a slingshot and a cruise time of something like 13 years. There are alternative windows later that require tours through the inner planets and push the trip beyond 15 years. The price? Billions of dollars and 2 decades until the first data arrive. But it's worth every cent. Fundamental science about how planetary systems are born and grow up. That leaves Neptune, the too-far place we've only seen up close once. Yes, in all of history, only Voyager 2 passed by in 1989. And it only managed that because it sailed a rare tide that repeats every 176 years. An alignment of Jupiter, Saturn, Uranus, and Neptune that allows, with one slingshot after another, acceleration without impossible amounts of fuel. Gravity assist works like a ramp. The probe falls into the planet's gravity well, and if it doesn't plunge in, exits on the other side with its direction adjusted and a speed gain drawn from a tiny fraction of the giant's orbital energy. It's the only realistic way to visit several destinations in one mission without carrying Titanic tanks. The cost? You almost never get to brake afterward, and if you want to stay, you need to bring a huge reserve of propellant just to reduce speed down to the planet's orbit. The math of braking at Neptune makes that crystal clear. The planet goes around the Sun at approximately 5.4 kilometers per second. Voyager 2, stacking assists, was flying at approximately 15.5 kilometers per second when it got there, almost 3 times faster. Capturing a probe in that condition requires a long engine burn, and the fuel needed for a vehicle the size of Voyager would be more than 10 times the weight of the spacecraft itself. The process doesn't happen in minutes. It would be on the order of 1 to 2 months of continuous braking for a light probe. Now imagine a crewed mission, large capsule, shielding, years of supplies, redundant systems. The deceleration rate would have to be much gentler to avoid subjecting astronauts to excessive forces, and the braking time could stretch to 2 to 4 years. Add that to the cruise and you're talking 24 to 28 years from Earth to Neptune orbit, even taking advantage of alignments and assists. And the way back? With current liquid chemical technology, the fuel required for a round trip would turn the vehicle into a propellant skyscraper. More than 90% of everything that lifted off would be tank, and we'd still be at the edge of the possible. That's why human missions to the fringes remain in the realm of someday, maybe with another kind of propulsion. Speaking of the fringes, we still owe the most famous ex-veteran of the bunch. Pluto. Dwarf planet? Yes. Irrelevant? Never. So distant that the sun looks like a very bright star. It makes slow, eccentric laps, sometimes approximately 30 astronomical units from the sun, sometimes near 50 astronomical units. For us, that becomes stubborn, chilly numbers. The Earth-Pluto distance usually swings between something like 4 and 7 billion kilometers, with light travel time ranging from roughly 4 to almost 7 hours each way. In other words, any command sent now only arrives many hours later. And the reply too. New Horizons, a small, light spacecraft, traveled for 9.5 years at 16 kilometers per second to capture images of Pluto's frozen heart. A crewed spacecraft, heavier and slower, would, in my view, need about 35 years to get there. 2 generations of astronauts taking turns at the window. Better choose companions you really like for that trip. In the middle of this whole tour, one detail keeps coming back. Far isn't just distance, it's energy. Changing orbits means changing speed, and every additional kilometer per second costs a lot. That's why answers like 4 months to Mercury, between 110 and 200 days to Venus, 9 months to Mars, a year and a few days on a Jupiter flyby, but nearly 6 years to orbit, 4 to 7 years to Saturn depending on the route. More than a decade to Uranus and Neptune, even in favorable scenarios, have to be read with the caption, "If the mission is a flyby, you go faster. If it's to stay, go slow and bring lots of fuel." It's also why gravity assists remain the fine art of space navigators. The difference between a passing snapshot and a long season packed with discoveries. Can we shorten all of this? Yes. On paper, there are paths. Solar electric propulsion, more economical. Tiny thrust for a long time, solar sails, a steady photonic push, nuclear reactors to generate continuous thrust, and bolder concepts like laser sails and next-gen ion engines. Each one solves a piece of the puzzle. Some cut cruise time, others make the required speed change on arrival cheaper. Engineering is advancing, mission by mission. Meanwhile, we keep stacking lessons that brought us here. The first close approach to Mercury, detailed maps of its crust, the Venera's heroic minutes in Venus's hell, Mars rovers turning pages of history, Juno's dives through Jupiter's field lines, Cassini's long opera among the rings, the single close wave at Uranus and Neptune, and the promise to return, carefully, methodically, ambitiously. In the end, the question, how long does it take to go, is less a stopwatch and more an invitation to understand how the solar system works and how we, stubborn primates with tools, learn to navigate this clock of gravity. Sometimes the answer is months, sometimes it's years, sometimes it's decades. And that's fine, because every minute spent on the road pays back centuries of knowledge when we return. So here's the nudge. If you could choose a single stamp to see up close, the shadow of a Saturn ring crossing the atmosphere, Europa's cracks, Uranus's calm, Neptune's storms, which stamp would you put in your cosmic passport?